Okay, we still have some technical problems, so but welcome to the first files in Typt 2023. Okay, so my name is Qianhua Bao. So I would like next each team, the team member, please introduce yourself and your team member. Okay. Let's start from the reporter first.
Hello everyone, for the business teams. And I'm Jason for the team leader. This is Brian, this is Amy, and this is Pearl. Thank you.
Okay, thank you. And Captain,
Okay, so we're from Taipei Legal Senior High School, and we're Waker Earthquake. So right there we have our team captain, Yang Chen-Xian, Shane Yang, and we have Zhang Nanxing, Nancy, and I'm Typt captain, Liao Junrui, Ray, and Zheng Naiyang, Nathan. Thank you.
thank you. Then the reviewer, please.
We are team faculty from China Yuzhong, and I'm the team leader Liu Jiawei, and this is our team member Chen Shiwen. This is Lin Xide. This is Liao Ziji. This is Geng Shengyou. Thank you, everyone.
Okay, thank you. Now I would like to introduce the jury. Start from myself. My name is Qianhua Bao. I'm from Zhongzheng University. Then Professor Zhong, please.
My name is 戴江钟戴江I'm from National Defense
电脑
University.
就是他说那个那一台的话，铁道
Okay, so my name
网
is
络时间不足。
So I'm from here, the National Taiwan Normal University.
So welcome everybody. I'm Cai Zishen from National Taiwan Normal University.
Okay. Thank you.
I'm Qian Yi. I'm from Zhongzheng University.
Okay, thank you. So we still need to wait our card maybe Thursday or Sunday. Okay, now?
我带到中间那一台，对，但是我可以用右边这台，对。然后我想要问一下，就是比如说你们可不可以用中间那一台？
他们是要哪条线？
就是连它，能不能连到中间那一台？就直接就是你桌上那条线，是中间吗？我刚刚试过了，在右边那台。对对对，啊，你们现在连一下，我把它切到中间那台，看能不能连上。对，如果能用那台的话，那我们就可以开始先用这台计时。 线有问题，还有线我缺一条，
缺一条线吗？
我一条线坏掉了，帮我找一条线。
啊，
老师听说接到我们那边去，但这条线坏掉了，对啊，我去拿去找，
可是还是要让他们可以。
对，那这个
我们有 HDMI 线，不需要。
OK， 就是那
够长吗？
没关系，我电脑可以搬去那边，整体码我整个。
麻烦这边是想要。
好的，看一下。老师，我这边有对不对？
这样可以，从那边控制。
哦，有。OK。有，谢谢。
要到那个餐饮那边。OK， great. Solve the problem. So, I would like the opponent to have 1 minute to pick a problem to challenge the reporter.
The opponent would like to challenge the reporter about problem number 9, oscillator school.
Problem number 9. Problem number 9. Oscillating school. So, reporter, you have 1 minute to decide.
We reject the challenge. We reject the challenge.
Reject. Okay. So problem has been rejected. So,
The reporter would then like to challenge problem number 6, magnetic oscillator.
problem number 6. So, reporter, you have 1 minute to decide.
like to reject the challenge.
So problem being rejected again. So problem you can pick up another problem.
Then the opponent would like to challenge problem number 4, colored lines.
Okay, problem number 4. Counter slide. So this you have 1 minute.
The opponent would like to reject the challenge. Reject the challenge.
Yes. Problem has been rejected. So opponent you can pick up.
Then the opponent would like to question problem number 8, Euler's pendulum.
Okay, problem number 8. Euler's pendulum. So this you have 1 minute to make it.
The opponent would like to accept the challenge.
Okay, problem has been accepted. Problem number 8, Euler's pendulum. So like each team, please write down your name for the presenter on the blackboard. Let's see. Opponent and reviewer.
我也从那个
你只要写就是名字，把他们名字记住。Reporter, you have 5 minutes. You have 5 minutes to prepare the whole story.
旅居的题目跟
对，要写那个要写现在旅居。
就是旅居，
他们现在是哪一题？他们现在选哪一题？好像是4名，这个要记下来。这个系统可以看到，我介绍到说，这个系统是我等下再来确认。OK， 它这个然后这个写在黑板上，语句还有这个。
Okay, time's up. Reporter, please take the floor.
Okay. Honorable viewers and fellow competitors, I'm the reporter Jason Lee from the physics team, Xinjiang High School. And now I'm going to report problem number 8, Euler's pendulum. So here's the problem statement. Take a thick plate of non-magnetic material and fix a neodymium magnet on top of it. Suspend the magnetic rod, which can be assembled from cylindrical neodymium magnets, underneath it. Deflate the rod so that it touches the plate only with the highest edge and release it. Study the motion of such a pendulum under various conditions. So here, in the next presentation, we'll mainly focus on does the plate's material cause an important influence on the magnetic rod, and how does the motion vary depends on different initial conditions. So here's our outline. We'll start with some of this observation video, then move on to our theory, then our experimentation part, and finally our conclusion. So here's the observation part. And this is our experimental setup. For the upper magnets, the magnetic field is 3,700 Gauss, and for the lower magnetic rod, the magnetic field is 3,500 Gauss. And we used an acrylic board whose thickness is 1 centimeter. And also, the static friction coefficient between the board and the magnet is 0.074. And here's the observation video. In our experimentations, we found that there are two kinds of the pendulum mode. The first kind is the normal pendulum mode, which swings back and forth like the video on the left. But also, if we apply a big enough angular velocity on the side when we push it, the pendulum will form a conical pendulum motion, which can be observed by the video on the right. So for some quantitative explanation, at first, the gravity and the hand push will force it to do the pendulum motion. And then the magnet attract and will form a check, and that is form a pendulum motion. But also, there might be some friction force to decelerate the whole motion. So here comes our theory part. First, we'll give some geometry and characteristic of the magnets. This is the schematic diagram of the system. For the upper magnets and the lower magnets, the mass is M1, M2, the radius is R2, the height is H1, H2, and for the magnetization, there are the capital M1 and capital M2. And here, we use multiple magnets to form one long magnetic rod. And also we can write the center of mass of the magnetic rod like this, using two of the angles. The angle theta is a function of the angle between the pendulum and the z-axis. And the angle of phi is a function of the angle of the pendulum between the pendulum and the xy plane. And here are some theoretical assumptions. First, we assume that there's no energy dissipated in this system. Also, we think that there's only one contact point between the bottom magnets and the plate. And also, the magnetization of the magnets remains a constant during the whole motion. And here, we will apply the Lagrangian mechanism to this problem. There are some reasons. The Lagrangian mechanism is equivalent to Newton's second law, but is from an energy perspective to obtain the EOM, which is the equation of motion of the system. The definition of L is the summation of the kinetic energy minus the summation of the potential energy. And because there are 2 degrees of freedom, which is phi and theta, which is phi and theta in this problem, so we'll apply it into the Euler's equation to get EOM twice. Apply it to Euler's equation twice to get the EOM. And here, the summation of the kinetic energy is the rotational energy, which includes 3. The first is the rotational energy of the theta, and the second one is the rotational energy of the phi. And also, the rod itself will cause a self-spinning motion. And for the potential energy, there are two of them. The first one is the gravitational energy, and also there's magnetic potential energy. And we set the lower surface of the plane to the zero potential plane, and we can then write the gravitational energy like this. And for the energy solving of kinetic energy, the theta, which is the angle between the z-axis and the rod, we can use some parallel axis theorem to get the moment of inertia of this function, this way of the spinning. And after that, we can get the rotational energy of theta of t, which can be written like this. And also, for the moment of inertia of the way that it spins around the phi of t, which is like it's spinning like parallel to the xy plane. The distance between the center of the single thin circular plate and the axis is the R2 minus R2 cosine theta, which is this blue line, and plus the H sine theta, which is this blue line. And after that, we can use some integral to solve the kinetic energy of the phi, but it is too complicated to be written because it is such a long. This is very huge, and also there's a self-spinning. Because we assume that there's no sliding, so the corner point will from here to here to here, and it will cause a self-spinning motion during the whole pendulum motion. And because when it spins one turn, when the theta of t spins one turn, the counterpoint will spin one turn too. So the angular velocity is also theta of t. And after that, we can get the moment of inertia of the circular rod and get the rotational energy of its self-spinning. And for the calculation of the magnetic potential, the interaction energy of two magnetic dipoles can be written like this. And after that, we'll apply it with some definitions of the magnetization, and finally write the magnetic potential energy like this. And here we assume the magnet a magnetic dipole. So after that, we'll calculate the kinetic energy and the potential energies respectively, and also put it into the Euler's equation to solve the yield and velocity. But it is too complicated, so we put it in Python, but my computer just stops working after that. And also there are some defects. For the first one, it is hard to estimate the affection of the friction because we cannot know exactly what is that a contact point or contact points. And for the friction, we don't know it is a static friction or kinetic friction or even like it is a rolling motion. And also, we have our hypothesis of the magnetic dipole is not that accurate too, because it is a magnet, not a single one magnetic dipole. So here comes our experimentation part. And here's the angular motion. So, as you can see, it is a motion like this, and also from like the theta of t is the when you swing like this, the theta of t is the angle p, and also you can see that it has it is some sort of spinning around the axis. This is the theta of phi. And here is the parameter of the length of the rod. For the 4 centimeters rod, the phi is only, the motion only lasts for like 1 second. But for the 6 centimeters one, it lasts for over 5 seconds. And as you can see, the shorter one has a relatively stable phi during the whole motion, unlike the one for the 6 centimeters. And this is the phi with and without initial angular velocity, which is like as I mentioned, we apply a force for a side to make it has with an initial angular velocity. And you can see that if it is without initial angular velocity, the system will, the energy decay will be bigger, so that the lasting time will be like under 6 seconds. But if it is with initial angular velocity, the motion will last for over 10 seconds. And for the friction dependent, for the parameter of the friction, if it is when there is no angular velocity, if it is with friction force, the motion will last longer because it is easier for it to form a rolling motion. And this is the phi with and without friction. Because it is with friction, so it has a more stable motion during time. And here's our conclusion. And we used this is my presentation. Thanks for listening.
Okay, thank you. Short question from our opponent, please. Okay, good morning, opponent and judges. Do you think is your upper magnet stick on your plate?
Yes.
So, okay, then why does your chart why does the original of your pendulum move? Like in page 22? Why does the center of the pendulum move?
Not 22.
Like the center, yeah. Maybe 22.
Like here, because it's not the factor of the upper magnet, it's only the factor of the lower magnets.
Okay. Then how do you measure your magnetic flux? How do you measure your magnetic flux?
Plus field or
Yeah.
field, just use a meter, magnetic field. Meter.
Magnetometer? Where did you put it? How far did you put it from the magnet?
Like, and as I mentioned, the distance, the thickness of our plate is 1 centimeter, so it is from 1 centimeter.
Okay. Then Have you ever considered that your plate have bent?
No, it is just not bent.
Okay, so is it a rigid body?
For the
Like-
port, we assume it is.
Okay, then can there be dissipation because of the bend? Or
We don't think so.
okay, then you assume that in page 10, you assume that your magnetic power is the same, magnetization is
Yes.
the same. But your pendulum, when there's a pendulum, the mass center moves.
Yeah.
Then I think that the magnetization does change. Can you?
We don't think it is a factor of about the magnetization.
Okay.
Okay, 那一张。So, opponent have the swimming protocol presentation.
Opponent, please take the floor. Okay. We're the opponents, honorable judges. Good evening. Today I'm going to be the opponent of this problem. So this is the problem statement, and we take a thick plate of the magnetic material and fix a magnet on top of it, and we suspend a magnetic rod, and we observe the pendulum, and the focus is on the parameters and explain this phenomenon. In the summary of the report, the phenomenon is that it swings back and forth normally, forms a conical pendulum motion when the initial force is greater. And the theory, they assume that there is no energy dissipation and there is only one contact point, and also that they assume that the magnetization remains constant. And they use Lagrange mechanism to analyze their system, and
they regarded kinetic energy as friction magnetic dipole moment. And their experiment, they use tracker to analyze it, but I think there isn't enough improvement to prove the theory. And pros and cons. The pros. They had clear force graphs to demonstrate the alleged theoretical model. And second, their equations are presented with well-rounded explanations. And the cons. They did not have enough parameters discussed, since a large part is ignored, I think. And the second part is that the theoretical model is somehow ideal, and it does not comply to the reality. And there is way too less experimental results to be analyzed to the theory. And then the line charts provided are somehow not clear to watch their theory, and it is too ambiguous. And the magnetic model is just, like I said, it's not fitted to the reality. So please. Okay, first of all, can you tell me the damping factors of your model, of your experiment?
We think that it is the effect of when our pendulum starts to from one side to another side.
Yes.
The friction will cause some energy decay.
Okay, so mainly friction.
Anything.
Okay, then how do you think your pendulum will decay? Like in a linear model or in an exponential model?
We didn't do an experiment about this, but I think it is exponential decay.
Okay, then did you investigate about the period of the pendulum?
Period. No.
Like how long it
No.
swing?
No.
Okay, so what's your mainly parameters again? What's the parameters you investigated?
About the field of theta.
Like the whole experiment.
What do you mean? We investigate
Like
about
you didn't investigate about the period. So what did you like?
So I'm going to explain the period in my experiment.
Okay.
Here it is with initial angular velocity and without initial angular velocity. So if you take a look at when it comes to 1 second, the one with initial angular velocity has 5 peaks, but only without initial angular velocity has only 2 to 3 peaks. So it is obvious that if it is with the initial angular velocity, it will cause a faster speed changing.
Okay. Then back to the damping part. Do you consider that maybe collision between the plate and the rod?
We don't think it is.
If it is inelastic, then will there be energy dissipation?
We don't think it is. There are collisions.
But apparently it bumped into the plate, didn't it?
But what our opinion is that the rod is always attached on the plane. So there's no.
It is always attached to one point or to one side?
point. We think it is to 1 point.
But when you swing it, I think there is a moment that it sticks to the plate.
Oh yeah, but it is but we have investigated about the feet because it is sort of spinning around the z-axis. So it won't be like any single moment that it has a plane attached on there.
Okay, so your pivot is always at one dot.
Yeah, 1 point.
Okay. Then does the friction really affects the model if it points at the fulcrum, at the pivot point? Right at the pivot point, isn't it? The friction.
Friction, like because we use sandpaper to
Okay.
add that friction force. So we like stick a piece of sandpaper when on the plate. So it will cause some because the friction force is very big.
Yeah.
Because it is sandpaper, so it will affect the rolling motion.
Okay, how does it affect?
Like because sandpaper it's not that even, so it maybe looks like this. So our pendulum is like this. So when it points from this travels to this one, the bumps on the sandpaper will cause energy decay.
Okay, so is the friction static?
Yes, we think it's stable.
So it doesn't slide at all?
We don't think so.
Okay, but you also discussed about the rotation axis, right?
Rotation, yes.
Does it change?
About which rotation axis? Like we have phi and theta.
Okay, can you analyze both?
So for the phi, we think that because the fulcrum is the track of a circle, and the counterpoint is travels here to here. So we think that for the phi here, the rotation axis is the perpendicular line, which is on the circle's center.
Okay, so can you tell me how did your data prove your theory? Like, how did you?
Because we didn't get a complete EOM, so we cannot prove.
Okay, so your
Right, but we
data
can
doesn't prove
we
it.
can know that some factors is caused we can know that some result is caused by a certain factor.
Okay. So, did you about the damping? I want to yes. Did you discuss about the damping in your theory?
No.
Okay, so the force remains the same. Okay. I want to talk about the board again. I think when the board is bent and when your circular motion moves on it, the energy there can be energy dissipation, but since you said that it doesn't affect your experiment or your theory, so like your data doesn't prove your theory.
You mean the bending of the board?
Like you didn't analyze that. How did you like fit your data into your theory?
We don't. Yeah, just like what I mentioned, I didn't get the EOM, the full equation of motion about this, so I cannot get a line like this from our theory because just like I said, my computer stopped working.
Oh, okay.
It is too complicated.
Okay. So why did your the one with the blue line, why did it stop from that dot? Did you stop recording or did you
What did it say?
like your blue line only stopped here?
Yes,
Can you tell me why?
and because it is because the force of magnets when it comes to like when the angular momentum is not big enough to hold the rotating motion, the force of the magnets is big enough to let it stop immediately.
Okay. Then can you tell me how did you set your camera when you're recording this experiment?
Right, just right below the angle.
Okay. Do you have a theory about why? Okay, this picture is fine.
Okay.
Okay. Can you tell me why the radius move, like the phi moves phi, like the center? There is a pendulum, right? And the
Yes.
center of the line can curve or
Oh,
has
yeah.
its own
Because
pattern. Right?
because we have this is the result that we only transfer the peaks.
Okay.
Yes.
Really transfer the heat.
Yeah, just like this initial a continuous data, but we only find the peaks.
Oh, then why did you connect them? Like they're continuous in time? No?
Yes. Like when it comes to another end, from this end to this end, we only record this end and this end. We didn't record the data points
Oh, so
for the
okay.
yes.
So the radius is the average radius between one period or half a period. Is that correct?
What do you mean by
Like since you average, I think you averaged your radius, or how
what
did
do
you
you mean by
get your
saying radius? What's radius in this?
like how did you?
And this is an angle.
Okay, so you connect these points together.
Yes. But if we don't add the points, it hard to observe because it looks like this.
Yeah, okay. So in my opinion, I think
Yes.
that it is better to use more data to get a clearer model, right?
Yes.
Yeah, and in my own opinion, I think that the period, if you investigate on the period, can you somehow like prove your theory? Or just support it? Because since I don't think your data really support your theory, because like it doesn't prove it.
Yes.
Right.
It is.
So I think you can investigate on the period, right?
For the period. That's a good point. But, so if we got the EOM, which may be a periodical equation,
Yes.
so it will show us the period.
Yeah, but
Yeah.
I think you still have a damping model here, like not really damping model, but it becomes closer and the density becomes higher here,
Yes.
right?
Yes.
I consider it as a result of damping. Then, like your experiment stopped, but you didn't actually talk about damping. If energy dissipation doesn't exist, I think it just goes forever.
It should be going forever. So we're going to find out where the decay comes from. Yeah.
Yes.
So we think that it is about the frictional force. So when the frictional force gradually affects the motion, the angular velocity will the torque will become smaller.
Yeah.
So when the time it cannot afford the force for the magnets, it will just instantly attract it and stop it.
Okay. So
here,
yeah, sure.
it just stopped.
The period went short at the last few seconds, right?
Yes, from this graph.
Yeah,
Yes.
so there must be energy dissipation here, I guess. And your
Okay.
theory, like,
Yeah, but we cannot, because the friction force is too, it is.
but you
too-
said it's static,
we think it's steady.
then is it constant in the whole experiment?
It is static friction. And
Yes.
it is a constant.
Okay, then I think you can actually calculate that. It's not complicated if it's constant.
But it is complicated to use in our theory.
Okay, so your theory doesn't really consider the
Right.
friction.
Yeah, I didn't consider it. Sorry.
Yeah. Okay, and in my opinion, except for the friction, I also considered like maybe the air resistance.
No, we don't think so. Because it is only 4 centimeters and 6 centimeters. The air resistance is maybe too small for a single rod.
Yeah. Okay. Then, if it is a friction, how do you think your damping will be?
Okay, I'm sorry, time's up. Summarize your discussion.
So okay, in our discussion, in our previous discussions, we considered that we did the reporter did not consider the damping and the collision as apparent, and their data doesn't support their theory, in my opinion. And I think they simply considered that there will be no energy dissipation, and I think it is not perfect. And their data failed to match. Yeah, obviously. And they also didn't consider the air resistance, which I think that it may be a factor. And I also think that they need more investigation on the period. And by doing that, you can actually kind of analyze it, or maybe without using the Lagrange system, I think you can simply analyze the force, like the gravity pull and the magnetic pull. Since it is suspended, I think the gravity must have worked something. Thank you.
Okay. The question from the reviewer.
I'm a reviewer and student. I'm the reviewer of number 8. So first I want to ask the reporter, what parameters affect the motion of the pillow?
For some like initial angular velocity, the friction force between the plate and the pendulum. and the length of the pendulum.
And the,
Can you state it? Sorry.
what parameters affects the motion?
I think the period, or maybe like the gravity pull and the magnetic force and the friction.
So is there decay of energy during the motion?
There is decay in our experiment, but in our theory we didn't consider it.
Okay, so can you tell me what factors?
Friction force.
And
I think except for friction, he just mentioned, I think there is also inelastic collision between the plate and the rod. And there is also somehow a little bit air resistance.
and then how many angular velocities do you think there are?
What do you mean by saying how many angles?
So in your model, in your experimental model, how many?
Three. There are three of them. The theta one and the phi and the self-spin.
And how did it change as time evolves?
Like in our theory or our experiments.
In your experiment?
In our experiment, the phi and the theta at first and it just stopped.
Okay, thank you.
Okay.
And does collision exist?
We don't think so.
And report.
I do think so when it's at the end of the
So
experiment.
then how would collision affect?
And I think it is elastic since it is a practical experiment. So it will definitely be energy dissipation as I mentioned previously.
Okay, thank you. In your experiments, is there air resistance, or is it the amounts necessary to consider?
That's unnecessary to consider it.
Okay, and
I think it is small too, but I think it was somehow.
okay, and so opponent, do you think that the reporter's experiments prove his theory?
No. Okay.
And do you think your experiments prove your theory?
No. No.
Okay. So how do your angular velocities change?
Change?
Yeah, how do they change over time?
Why? Because energy decay.
But you had 3 angular velocities.
Solve the concept. So before you have 2 minutes to prepare the presentation. Okay, review, please take the floor.
so I'm going to do my remarks on this. Yeah, so first, the pros of the reporter are the reporter provided very clear observations and also explained his theories very well. And also he had very clear graphs. But the cons are there are no quantitative analysis between the experimental results and the theoretical results. And also the line charts and the lack of experimental data. And the opponents, the pros are that he asked the direct questions. And the cons are that the opponent focused a lot on theoretical assumptions that the reporter made. But as the reporter said that he didn't consider it, but he just kept talking about it. And so the first question is that the opponent asked about the damping factor. And the reporter answered that the reporter answered that friction will cause damping effects. And I also think that friction will cause damping effect, but there are also air resistance and other factors that will affect. And then the opponent asked how you think it will decay, and the reporter answered that he didn't consider energy decay. And the reverse thinks that he should have considered energy decay. And then opponent asked the parameters of the experiments, and the reporter answered the initial velocity. But the reviewer thinks that there are also a lot of parameters, like the length of the rod and the magnetic force. And also, the opponent asked the collision between the rod and the plate. The reporter answered that he does not think there are collisions. And the reviewer thinks that there are inelastic collisions that can have energy decay. And the opponent asked, does friction, is the friction constant and affecting the motion? And the reporter answered that he did not think about friction, but it will cause energy decay, and I also think that. And the opponent asked, can the reporter prove the damping from the data? And the reporter answered that we can't. They can't prove it. And also I asked that what are the main parameters of the Euler's pendulum and how do each affect the motion? The opponent answered friction and length of the rod, and also the reporter answered the gravity pull and the magnetic force. And I also asked what factors affect the decay of energy, and the opponent answered friction. The reporter answered also there are collision and air resistance. And the reviewer, I asked how many different angular velocities are there and how do they change as time evolves. The opponent answered 3, and he didn't say how it evolved. And
I'm sorry, time is up. Okay, the concluding remark from the reporter.
So here's the reporter. So for the concluding remarks, for the theoretical ones, first, we could have tried to simply use force analysis, which is recommended by the opponent, because Lagrange model is to prevent the stop working of my computer because it is too complicated for the energy perspective. And also, we could do more investigation about the energy dissipated, like from the friction force or the bending of the board or some other factors. Also, we missed the investigation about the period over time because it might also related to some energy decay. And also, we should get the complete EOM, the equation of motion, to check if the experimental results could prove it. And for the experimental ones, we could have record the period by doing, and also we could do more parameters like the strength of the magnets, and for like, yes. And also, we should record more data during the motion, not rather than only recording peaks, because it might have something related to our theory. But we don't think some minor factors will affect our experiments much, like the air resistance or some changing magnetizations. But we could try to investigate about it because it might somehow still has an influence on it. And I'm going to thanks for the opponent and the reviewers recommend, or the opponents and reviewers recommendations. Thanks for listening.
Okay, thank you. A question from the jury.
Please go to the video, page 22, the video. Show us again. There is a video, actually. Okay, you see, it's raining big and gradually it goes slow, right?
Yes.
To the
right one.
to the figure.
Okay.
You see, you try to figure out, you measure the maximum point tilt, right?
Yes.
It almost all the same. It did not decay.
Like the blue one.
Means, from the figure, you always oscillation in this way.
Yes.
But your video showed. Okay?
Yes, so this is the graph of phi, and it is the rotation around the z-axis. So maybe it is because when it comes to this here to here, it is...
No, I'm telling you, I'm not asking your measurement. When I observed it, I saw it swing back and forth with large angle and gradually go to small angle.
Yes.
But your data, you say you made the measurement. Right, you made the measurement. But it did not coincide with the experiment observation.
Right,
Okay, let's see like, almost everybody is going to 0.5 to 1 around that, right? And almost like the same. But when you see, especially this one, because it decays so quickly, right?
Yes.
It means the angle should be.
But the direction is still here. But we're not going to investigate about the amplitude. We're going to investigate about the angle.
Let's say.
Like this is. Yes.
Let me tell you one thing.
Okay.
You swing, the in swing, then I say the angle is the same.
Yes.
Are you making the right thing?
Yes, because it is not a theta.
I'm seeing from this angle. I'm not watching this. I'm watching this.
Yes.
Does it change the angle?
No. Like we'll analyze this.
Go to the next one. The opponent. You said the gravity played a role, right?
Yes.
What role?
Because it gives a torque to the rod.
What kind of role?
Sorry?
Because it's a swing,
Yes.
right?
Yes.
Gradually the swing, the gravity will play a role, same as we thought. Can you tell any difference? That is so different from our thinking.
Can you please restate your comment?
Okay, let's swing, let's put a particle here. It goes to swing, right? It's due to the gravity.
Yes.
True. But it's still the gravity. But is there anything different from this kind of role?
Yes, it spins like this either. So it goes.
Still the same. Okay. Never mind. Can I ask the third question? Actually, no.
I will examine first.
Okay.
One more question.
So you all mentioned about the damping factor, and the most important thing should be the friction. So usually the friction is there should be some kind of relative motion. But in this case, can you describe clearly what is the intention of such kind of relative motion from reporter?
Like because there's huge friction force. So when the counterpoint travels from here to another point, it will you will experience huge friction force and costly.
If the friction is bigger, I think the pendulum will stop faster.
I mean, what is the origin of the friction? Or what is the intention to be relative motion to cause this friction?
Because the two surfaces simply touch each other.
Yeah.
Of course, it's caused. And I think if the friction doesn't only affect on the pivot spot, and instead it is not considered as one dot when it is going on a pendulum. Instead, there are like a small surface here. Then the friction will not work on the pivot. Then somehow, eventually it will stop the pendulum. Okay, the time's up, so we go to the grading. Go to the scrolling section and start from the reporter first. So you please raise your 47665. Then opponent. Seven, 77767. Then reviewer, please. 68777. Okay. Anybody want to say something about your score? Okay, I gave a little low rate for the reporter. I think you need to you give a fancy model, but the model it looks like the model is no use to your experiments. Okay, so you do your experiment, then find some model, try to explain your what you watch. Okay, so I think that's something you probably can do better. Okay, close. Let's take a. I think we can take a 10 minutes break. Before you leave, please move your table to the next one. Get everything ready. Especially check your computer and the video. Okay. Okay, let's start second fight of this round. Okay. So I would like to ask the opponent pick a problem to challenge the reporter.
challenge question number 1.
Problem number 1, practical physics. 1 minute to start.
The reporter accepts the challenge.
Okay, problem has been accepted. So, total you have 5 minutes to prepare your question.
Thank you.
Also, please write down your name for your presenter on the blackboard.
Sorry, I don't think the timer is working.
Timing.
That's all.
Okay.
Next.
Problem is
One.
what? Okay.外面不会没电池。有，不是没电池，他们都有。
please stand.
Honorable judges and worthy opponent reviewer, I'm Zhang Naixing from Uyghur Private High School from Uyghur Erday. Today, I'm going to present problem number 1, freckle fingers. First, I will introduce the phenomenon, theory and experiment, and we will summarize the presentation at last. And the problem statement is, the effect of freckle fingering can be observed if a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. How are the geometry and dynamics of the fingers influenced by the relevant parameters? And our focus for the presentation is investigate the relevant parameters and analyze the geometry of the fingers. And at the right side is our demonstration video. You can see the ink alcohol mixture deposited on the diluted acrylic paint, and it will form freckle fingers. And at the right side is ink alcohol mixture droplet, and at the left side is pour ink droplet. And you can see that the alcohol plays an important role in the phenomenon. And here is our experiment setup. At the left side is diluted acrylic paint, and it is made out of pouring medium, which can make the liquid more fluid. And it is also made out of white acrylic color. And at the right side is ink alcohol mixture, and it is made out of black acrylic paint, black acrylic ink, and isopropyl alcohol. And we use pipette to control the volume of ink alcohol mixture to 0.01 milliliter. And at the bottom is ink alcohol mixture deposited on the diluted acrylic paint. And I'm going to introduce how we uniformize the thickness of diluted acrylic paint in a minute. And first, we will place the paint on a transparent plastic film and use another transparent plastic film to smooth and spread the paint out. And we will repeat the step 2 until it is uniform and commutative. And at last, we will make sure that every transparent film and the paint is the same size and the same weight. And I'm going to introduce the terms we will use in the presentation. And the red circle is inner circle. The blue area is outer circle area. And the yellow area is finger area. And the purple line is finger length. And the green line is the whole circle. And for the data analysis, we first turn the image into 8-bit and use image color picker online to define the boundary between like black and white and the inner circle or outer circle area. And we will use image J to measure the length and the diameter. And I'm going to introduce the theory. And first is Marangoni effect. And Marangoni effect is the mass transfer along an interface between two faces due to the gradient of the surface tension. And as you can see, at the center of the picture is low surface tension, and at the rim is the high surface tension, which caused by the evaporation of alcohol. And the phenomenon will, the droplet at the center will break into tiny droplets. And it is a compare of Marangoni bursting and freckle fingers. The similarities are the droplet is both ink alcohol mixture. And the theory behind the phenomenon is the differences in surface tension and vapor pressure results in the phenomenon. And the differences are in Marangoni bursting, the base is oil, while in freckle fingers, the base is diluted acrylic paint. And the phenomenon of Marangoni bursting is it will break into thousands of tiny droplets. And for the other is freckle fingers. And the second theory, we are going to introduce the viscous fingering. And viscosity is the resistance of a flow. So the higher the viscosity is, the smaller the fingers are. And the diffusion of the fingers is random, hence it is unpredictable. And it is a theory about the surface tension and the radius of the droplet. And you can see And the result is that when the surface tension increases, and the radius of the droplet will decrease. So in the Marangoni effect, we talked about the evaporation of the alcohol will make high surface tension, and high surface tension will decrease the radius of the droplet, so it will break into fractal fingers. And here are our experiments. And first, we change the time interval between diluted acrylic paint and ink alcohol mixture deposit on it. And we can see that with time interval rising, the inner circle, whole circle, and fingers length will decrease. And it also matches our theory is that when the time interval rises, and the viscosity of the base will also increase. And when the viscosity increases, the fingers will be smaller, and the diameter of inner circle or whole circle will also decrease. And it is a picture of the fingers under microscope. And we can see that it is more, the length of the fingers in 20 minutes is more smaller than it is in 5 seconds. And the next parameter is about diluted acrylic paint concentration. It's the concentration of pouring medium in the diluted acrylic paint. And as we mentioned, the pouring medium can make the liquid more smooth, and so does it make the decrease in the viscosity, which will make the increase in the inner circle, whole circle, and fingers length. And it also match our theory. And it is the picture of the ratio of acrylic paint to pouring medium. And the length difference is also very obvious. And we can see that in this picture, the 1 to 4 picture is the fingers in 1 to 4 picture is more bleeding and unclear to 1 to 1. The fingers patterns is more unclear, but it is hard to define that it is bleeding or unclear. So we use the parameter per length to define it, and we can see that when the pouring medium concentration rises, and the parameter per length will decrease. So it also matches the theory and the pictures. And I'm going to talk about the isopropyl alcohol concentration. And you can see that when isopropyl alcohol concentration rises, and the length of inner circle, whole circle, and fingers will also rise. And we think that it is because when they have more alcohol, and the amount, the time the alcohol needs to evaporate is longer, so it can expand more wider than when the alcohol concentration is low. And we can see that in the ratio of ink to isopropyl alcohol is 1 to 10. And the fingers are more lighter because the ink concentration is decreased. And I'm going to talk about ink alcohol mixture volume. And in this picture, we can see that the fingers length keeps stable. And we think that is because the ink will grow into the fingers area. It will cause the inner circle, whole circle diameter to become bigger. And so the fingers area will become larger. So the ink volume will go into the fingers area, but not grow in the fingers length. And it is the isopropyl evaporate time. And you can see that the time we place the ink isopropyl alcohol mixture in a container, and we use the different time of it to do the experiment. And we measure the inner circle, whole circle, and fingers length. And we can see that it has no obvious difference between the difference in the time. So we think that the isopropyl evaporate time in the container can be ignored in the experiment. And is that we use various alcohol to do the experiment. And the results are that if the alcohol cannot merge with the ink, so it will not form the fractal fingers. And the example is the pentanol, and it did not form fractal fingers, but others did. And it's the temperature, and we differ the temperature, and we can see that below 40 or 50 temperature, and it has no obvious change, but above 40 Celsius degree, and it has a obvious change. And I think it is because that when we are heating the ink alcohol mixture up, and it will make the evaporate of the alcohol and more faster. So it will make the results are like the decrease of the alcohol concentration. And in summary, the patterns of the fractal fingers form randomly, so it cannot be predicted. With the viscosity decreasing, the circles will be bigger and the fingers will be more bleeding and larger. This is the perimeter per length. Volume of the droplet will cause bigger circle with a similar finger length. Evaporation time of the alcohol can be ignored. The alcohol which is not merged with water cannot cause the phenomenon. And the temperature will not impact the patterns. Thank you.
Okay, thank you. Opponent, you have 2 minutes to ask some short question.
Okay, I'm the opponent from Team Chocolate, and first I would like to ask, like you said, you use the same weight and size of acrylic ink.
Yes.
So how do you measure and ensure every time you do experiment is the same?
And first, we will make sure that the transparent plastic film is the same size. And we will make sure that the paint on it is the same weight. So we know the thickness of the paint is the same.
Okay, so do you consider the acrylic ink isn't flat? So it's there's something that go up in the surface.
So we will repeat the step 2 to make it to be uniform.
But in your video, I just see that you do the step like this, and the outer part just like there's just some like line.
And yes, we measure the weight at the net when we complete the step 2.
Okay. So do you like you use like long time, like for 10 minutes to observe phenomenon. So is there any problems like the ink just go dry?
Yes, it is what we want to see, is the paint to go dry. And we can see if there is viscosity difference in it.
Okay. So
I'm sorry, your time is up. So opponent, you have 3 minutes to prepare your presentation. Some announcement, you are not allowed to use the cell phone to take a picture or recording any video, especially for other presentations.
就打。
Okay, opponent, please start.
Okay. Okay, so I'm an opponent Chen Shiwen from Team Chocolate, and today I oppose the problem number 1 fractal finger. Okay, so here's the problem statement. The effect of fractal finger can be observed if a droplet of alcohol mixture is deposited onto diluted acrylic paint. How are the geometry dimensions of the fingers influenced by the relevant parameter? So here's summary of reporters and pros and cons. So here's observation video. The process clearly shows the phenomenon in good breakpoint focusing. And they use Marconi effect. And cons is lack of theoretical explanation and use oil acrylic paint approximation. And here's experiment. You use diluted acrylic paint with this white and black and pipette and transparent plastic film to set up. And process creative setup and clear result of image. But cons is no quantitative comparison between different parameters, and didn't show the relative length comparison in the result, and didn't show the length and area were calculated. In conclusion, great theory and experimental results, but lack of quantitative analysis. And process clear concluding summary. The cons is didn't show full image, only the endpoints made in so that length can be seen relatively, and no quantitative analysis. So here's opponent's question. So like first, so this is my questions that I will like to ask. So okay, you please go to the next page. Okay, first, can you turn to the page that you write theory?
Okay.
It's very fun. Okay, yes. So, next page, please. So in this is the oil dot, and this is the oil acrylic paint. But how?
Oh, I can explain the more clearly. And the base, the center, the place is oil, and the blue dot and the droplet is ink, alcohol ink mixture. So the experiment is that ink alcohol mixture will deposit on the oil, and it will break into the mixture will break into tiny droplets.
Okay, so it seems there's some difference between your theory and the fractal finger. So how do you think the why? Because you said the macaroni first thing is the dot, but fractal finger is orange fingers.
We think that the diluted acrylic paint is porous media, and the oil is not. And the viscosity between the oil and the diluted acrylic paint, and it also will form the differences of the phenomenon.
Okay, then. Okay. And like you said, in your conclusion, you said the fingers forms randomly, right?
Yes.
It's unpredictable. But what is the cause that you think the finger will form?
We think that our finger form is the lens theory, and we say that when the surface tension increases, it will cause the radius of the droplet to decrease. So it will form the width of the fingers, and it will become more smaller. So it will form fingers.
Okay, but why less spot? Like your surface is here. Why does this spot form the fingers? And the spot right next to it here.
And so we say that it is randomly and it is it is unpredictable because the diffusion in the phenomenon is very random.
Okay, then can you please turn to page 21? Okay, I would like to know why does like you said 1 by 1, 1 by 2, and 1 by 3. Sorry, there's different like black area. Why does it?
And so you mean the black area and what is the difference between the?
Yes. So why? So like here, the black area just go to like the end of the finger, but here is, and here just like even no black area in the name.
Oh, it's because that, and we have mentioned when the diluted oxygen concentration rises, and it will cause the finger's length to also increase. And we can see that the finger's length in 1-to-1 is only this small, and in the 1-to-2 is the finger's length will almost to fulfill the picture. And in 1-to-4, we cannot use the microscope to fully picture the finger's length. And it will break into many small pictures to form a complete fingers because the length is too large and we cannot see the complete fingers in a microscope.
Okay, then I would like to ask why there's why there's like the end of the finger is the spot of like black, but here it is.
It's because that, yeah, we have mentioned it, and I think it's the diffusion is random, and so we will not know where the ink will go, but we know that it will form fractal fingers, and so maybe here is more white and here is darker, and it's caused by a randomly phenomenon.
Okay, then why here's but okay, you said randomly, but it randomly formed in the spot. But why? Why will it just cause black? It's not randomly. It's just some reason. Why? Can you tell me?
Because can you restate the question?
It's like you said the finger just formed a spot on a random spot, and like I'm interested in the black area. Why does it form like black? So you said the reason like why like here has a black ink, I think it's ink. Here's black ink. You said it's caused randomly, but why? It's a random space. No, the random spot. It forms in random spot, but the reason why it forms.
The reason why it forms is that we can see it is the outer circle we have mentioned it, and behind the outer circle it will form the fingers, and because the ink is black, so it will form the black fingers, and it will break into by the, you can see the surface our theory about the surface tension and the radius of the droplet. So when the surface tension is too high, the radius of a droplet will be very, very small, so it will break into the fractal fingers.
Okay, then can you please turn to page 24? Okay, so like the ratio of ink and alcohol. So the same question: why does the ratio of alcohol rise and like there's black and here's green, and here even then it have the black in the end one?
Because what caused the fingers to be black is the ink. So in the we change the ratio of ink to isopropyl alcohol, and this picture, the isopropyl alcohol concentration is very high. So the black ink is the concentration of the black ink is very low. So the color of the 1 to 10 will be more lighter.
Oh, so you think like the ability of the alcohol carry the black ink to move on? You mean like that?
And what causes the fingers to move on is the surface tension gradient. And we mentioned it in the Marangoni effect is that when the alcohol evaporates, and it will cause high surface tension. And at the center of the circle, there has more alcohol, and so does the low surface tension. And the liquid will go from the low surface tension to high surface tension. And when the alcohol is still exists in the ink alcohol mixture of the fingers, and so does it will keep expanding. And when there is no alcohol, so therefore no surface tension gradient, and it will stop to expand.
Okay, thanks. Then I just asked in a short question. Like you say you want to observe like the ugly paint just go dry, become dry. So can you like measure the rate that it becomes dry?
And we think that it is the time caused when the time rising, and it will become drier, and the viscosity and the experiment results can also see that.
Okay, but can you make sure that every experiment it has the same rate of drying?
Yes.
Yes, but
But because drying is related to the thickness, we control every thickness, and the transparent plastic film is the same. So the drying ratio of the time is the same too.
but can you but like the drying is the water comes out of the paint, but it is relative to the moisture of the air.
Yes.
So do you mention it? Do you notice
And
it?
we conduct the experiment in the same environment. So the moisture of the environment is the same.
Okay. Then, so how do you calculate the finger area and length?
And you can see that we use in the data analysis, we turn the image into 8 bits and use image color picker on one. And it's not obvious, but it has lighter and darker area. And we use the image color picker to see the RGB number of the color. And we define that when the RGB color is 60, 60, and 60, and it is the boundary of the outer circle area and the inner circle. And then we use image J to measure the diameter and the length of the circle and the fingers.
Okay. Then, oh, can you please turn back to page 24? So, so I would like to ask the question is that, like the length here to here is same with here to here?
Yes.
Yes.
We make sure that the scope of the microscope is the same.
Okay. Then like 21, page 21. So is here same too?
Yes.
Okay. Then let me see. Okay. Page 7, please. Page 7. Okay. Like you said it's flat, right?
Yes.
Okay, but can you really sure like the plastic film you just transparent it is really flat, the surface?
Yes. We smooth and spread the paint out, and we make sure that it is uniform and flat. And we keep doing the spreading until we make sure it is.
Okay. Then.
Okay, time's up. I'm going to summarize your discussion.
Okay, so here's the So here's a conclusion. Here's a good graphical and experiment result, and the image shown lack relative length comparison, and didn't have quantitative analysis. And in the discussion, me and the reporter discussed about the question like why the finger has why the black area forms in different places and how does it form, the reason why, but not just like explain in it forms randomly. And we discussed about the difference between the Marconi bursting and the fractal fingers. Oh, time's up.
Question from the reviewer.
Hello, every jurors and fellow competitors. I'm the reviewer from the physics team, and I want to ask the reporter how to define a finger.
We do not define a finger. We replace the definition to the perimeter per length. So we can see that when the perimeter per length is larger, and it will more clear the finger is. But we say the finger is the phenomenon. So we do not really define what a finger is.
And the opponent, how do you define a finger?
I don't think what reporter can, how they define, but I think that just some region that just go off the surface that called the outer circle. I don't really remember it. Just I think that can be called as finger too.
Okay. And I want to ask the reporter, could you turn to a page that about your experimental setup? Yes. And I want to ask, does the size of the droplet affect the fractal finger?
No, we don't think so. Because the phenomenon starts when the droplet is deposited on the paint. So we do not think the velocity will affect the paint to expand or form fingers.
Okay, and could you turn to a page there about the fractal finger? The fractal finger. Yes. And I want to ask why there is a white space between the outer circle and the inner circle.
And the white space between the outer circle and the inner circle is that in the Marangoni effect, we mentioned that it will cause surface tension gradient, and it will force the droplet and inside the circle, in the inner circle will expand to the outer circle area. So it will form that the black ink just expand to the outer circle, and only a few will stay in the inner circle, and it will make the color white.
Okay, and do you consider the friction of the ink and between the acrylic pen?
We think that the friction between the ink and the acrylic pen is that maybe the viscosity, and so we just discuss it in the experiment and theory.
Okay, time's up. So you have 2 minutes to prepare.
the physics team, and I want to talk about the performance of the opponent and the reporter. And let's talk about the reporter performance. And the pro is good delivery and clear show the phenomenon. And the cons is it doesn't consider the effect of the evaporation and the dropping height. And some and the opponent's performance. The pro is he asked the crucial problem, but the cons is he didn't ask about the theory and didn't provide the better solution and the reason about some questions. And the discussion part, the point raised by the opponent is what caused the fractal finger, and the reporter's response is the randomness of the mixture. And we think that the mixture is well mixed, and the randomness is caused by the dropping. And my question is, what the definition of a finger? And the reporter, she didn't answer. And the opponent think that the outer circle part that you can define a circle, you can define a finger. And I think the opponent part is, I agree opponent's opinion. And next is my question. I asked, does the dropping height affect? And the reporter responds no. But I think if you adjust the dropping height, it may cause the alternation of the fingers. That if your dropping height is too high, and when the drop test go down, that the fractal finger may not appear. Thanks for your listening.
Thank you. Concluding remarks from the reporter, please.
First, I would like to thank all three teams and the jury, and I appreciate the opponent and the reviewers to ask the questions about the experiment and the theory, and I can be more clear to the experiment and the theories. And the concluding remarks are I need to do further improvements is that the quantization of evaporation as a factor. And I need to discover more approaches to effectively quantize the observed results. And the definition of a fractal fingers, I think, is presented clearly on the slide. And we talk about that the outer circle area and the inner circle area and the fingers length and finger area. And I think I clarify talk about the fingers and last slide. And about fractal finger, I think it can't be defined because you can't define that. You don't know and the length and the width. What should a finger to be? So I think it's impossible to define a finger, but I can define what fingers are. Thank you.
Okay, thank you. So, question from the jury. Okay, please.
You demo the video that the declaration of droplets. That is one. Did we see everything? This one. Next one. There is how you evaporate. Yes. It seems to me there are three periods. One period is the figure out, right? The second, actually, is spread out the first, then the figure out the second place. Later, the figure goes another figure out, right? can you tell why there is a three-stage, especially even they are not evenly, but for some reason, the size of the finger almost around the range and almost around some kind of distance, it was spread out, right? Have you ever tried to quantize those, what's the range of this one and what's the range of the third phase? Because it's go to a smaller thing road again.
Actually, we have measured the velocity, the circle extent, and where the circle extends. But we can find any similarities in the critical velocity is grow fingers. So I did not prove. We assume that it has a critical velocity to let the alcohol mixture break down into fractal fingers. But in the experiment, we cannot measure that, and we cannot find the critical velocity. So we do not put it in our presentation.
Okay, so I would like to ask the reporter first. So what is the physics behind for the Marangoni effect?
The physics behind the Marangoni effect is the surface tension gradient, and it will cause that the droplet from low surface tension to high surface tension, and also the theory about the surface tension to the radius of the droplet. And when the surface tension increases, it will cause the decrease in the droplet radius.
Okay, so you say the diffusion is random. Do you think the diffusion is important?
Yes, it is important.
Okay, so do you think that the diffusion is important?
Do I think the diffusion?
Yeah, diffusion.
I think the diffusion is important too.
Okay, so what kind of the driving force for the diffusion?
Sorry,
Driving force for diffusion. Okay, same question back to here.
About the driving force of the diffusion.
Yeah, what is the driving force for diffusion?
It's about the surface tension.
Okay.
We think about the driving force to the circle extent is that it has an angle at the rim of the circle. So the gravity will make the circle to expand.
Any other? Then we go to the scope section. Okay, let's go to the scope section. Scope for the reporter first is raised 79788. Now for opponent. 6, 6, 6, 7, 7. Now for reviewer. 6, 7, 5. 6, 5. Okay, anyone want to make some comment? Okay, yeah.
Driving force for diffusion is concentration. Okay, that's all.
Okay, thank you. Let's take a 10 minutes of book.你们是4个人还是4个？OK， 好。OK， 大家都回来了。Okay, everybody here, so let's start the last 5 of this round. Okay, so I will ask the opponent pick a problem to challenge your proposal.
The opponent would like to challenge the reporter problem number 15. Pancake rotation.
Problem number 15, pancake rotation. The reporter, you have 1 minute to make the mistake. Problem has been accepted. So, reporter, you have 5 minutes to prepare your presentation. Also, everything please write down the name of your presenter on the blackboard. Okay, reporter, please.
I'm from Team Sovereignty, and I'm going to be presenting you number 15, pancake rotation. So first is our outline. We'll introduce to you the observation, and then we'll talk about the theory, and then the setup and tools, and then the experiments, ending with the conclusion. And so first the introduction. When we place a few balls in a round container, and if you move the container around a vertical axis, the balls can move co-directionally with the movement of the container, or they can move in the opposite direction, which is different from the movement of the container. So I'll explain this phenomenon and investigate how the direction of movement depends on the parameters. And so the key question is, will the amount of balls affect the motion of the balls? And which parameter will affect this phenomenon? We have three: angular velocity, the size of the balls, and the bottom area of the container. And so this is our observation video. You can see that when we have fewer balls, this is co-directional motion. And when we have more balls, you can see that this black ball is moving this way, while this is rotated this way. So this is opposite directional motion. And so is the theory. Here we use Fc as a centripetal force, AD as a dense area, and AL as the loose area. And friction is F, angular velocity is omega, and radius is R. So the centripetal force. When moving the container around a vertical axis, the container will have centripetal force, which is this when it's rotating toward the center of the circle of rotation. And now the friction force, it's normal force times friction coefficients. And then because friction coefficient is only related to the contact surface, so when the normal force increases, the friction force will also increase. And the friction force always resists movement trends. And now the coverage rates. So the coverage rate is the ratio of the cross-sectional area of the balls to the bottom area of the container. So when we have a container with balls, the full container area is pi r squared, big R squared, and the small balls, the largest area, 2D area, is pi r squared with the small r. And so our prediction is when the coverage rate of the balls is higher, the opposite directional motion will happen. And vice versa, when the coverage rate is low, the co-directional motion will happen. Okay, so when we cut the circular motion into 4 parts, rightward, downward, leftward, and upward, centrifugal force. So first we are going to talk about the co-directional motion. So when the container is rotating, it will have centrifugal force, like we said before. And because of the inertia, the balls will be likely to go opposite of the force, which is this, and they'll be cramped up here. And then when the centripetal force is when we change it upward, then it will keep rotating this way. So the ball's here, we're here, and then now they become they place here. So that's a rotational movement seen. And when the centripetal force is this way, the same thing. So the balls will move this way, which is the same direction of the movement of the plate. Now we're going to talk about the opposite direction motion. So when the left where the centripetal force exists, this is first. So everything will be pushed to this side of the plate. And then let's focus on this black ball. So the black ball will have a friction force with the outward of the plate. And because there are a lot of balls, so the friction will increase, and the balls in the container can be divided into, here this is the dense area, and here is the looser area, which is AD and AR. So now when the centripetal force is this way, then due to the higher friction, balls in the dense area will not move easily, so they're likely to move less than the loose area balls. So this either stays here or moves just a little bit upward, so opposite directionally with the centripetal force. So now in similar fashion, when the rightward centripetal force exists, the balls in the original loose area will move opposite directionally with the centripetal force. And actually the black ball here is in the loose area. So now this area is free to move for the black ball. So now when we move to the next page, the black balls get pushed upwards because the centripetal force is down there now. And now we see that the black ball is moved upward. So we can see that we rotated this way initially, and the black ball ended up here. So the black ball moved like this. So that is an opposite directional motion. So now is our experiment setup. Here we use Lego blocks and an EV3 to make sure that the omega of the experimental setup is constant. And we put a black ball here so we can track the data easily. So we used tracker to measure the angular velocity, and then EV3 to generate the constant angular velocity. And then we used Excel to create the graphs. So first is we set an EV3 right here, and we used Lego blocks to fix it right down here. And then we placed the Petri dish at the middle of the rod. So then we placed many plastic balls into the dish and turned on the EV3 to observe and record its movement direction. These are the sizes of the experimental devices. So radius of the round container is 4.5 centimeters. So it's this dish that is 4.5 centimeters in radius. And then the small, we have three different balls in size. We have small balls with 0.5 centimeters, medium with 0.7, and large with 0.9 centimeters in radius. So the radius for this is the ball, and this is the radius. So we have our results of, also the omega we use here have been put as low and high with 200 degrees per second and 400 degrees per second. So now we have covered rate of small balls in the dish is 0.012 n, and n stands for the number of the balls. Same for the rest. For medium balls, it's 0.024 n, and for large balls, it's 0.04 n. So we can see that large balls have higher coverage rates than small balls per ball. So in our results below in the table, the plus sign stands for co-directional motion, which is moving the same as how the dish is moving, and negative stands for opposite directional motion, which is the opposite. So now for small balls, in higher omega, which is 400 degrees per second, the coverage rates ranges from 43% to 48%, about 48%. And we have 35 to 39 balls here. So when we see the coverage rate is small, both high omega and low omega have co-directional movements, while when we get to higher coverage rates, these are negative, which is the opposite direction. And for medium balls, mostly the same happens, except for 50.82% here. In high omega, we have a co-directional movement. And for large balls, 53%, we have a low omega co-directional movement. So when we graph these dots, we have coverage rates versus radius. We have 0.5, 0.7, 0.9 for small, medium, and large balls. And here we have a trend of high omega. So this is high omega, and we have a trend of high radius, higher coverage rates. And low omega is the same. And so when the ball's coverage rate isn't less than the minimum ball counts, that will let the balls move in the opposite direction. So basically, when the ball's coverage rate is lower than the minimum ball counts that we have, the minimum ball counts then, which is basically a boundary condition. So that will let the ball's movements be opposites. So we can see here that these are opposite directional movements, same for these and these. So these exceed a coverage rate of about here. And so our conclusion is, the phenomenon is when putting a few balls in the container, the ball will move co-directionally with the container, or the ball will move in opposite directions. And this is based on a coverage rates that we can see. And the reason how the balls move is related to centrifugal force and friction force, which is pointed out in the theory. So when the opposite motion happens or not is not related to the coverage rate, is related to the coverage rate of the balls. So higher coverage rate is opposite motion, while lower is co-directional. And when the coverage rate is higher than the limited amounts, the opposite directional motion will happen, and vice versa is the same. And the angular velocity of the container does not affect the result too much. So we can see the trends are basically the same for high omega and low omega. And then for our experimental experiments, we have corrections, and the errors came from these 2 points: the collision of balls in the container, and also the surface of the container isn't too regular. Okay, thanks for listening.
Okay, thank you. So short question from the opponent.
So here are some short questions from the opponent. So first, what friction force do you think is in this phenomenon? Is it a static friction or it is a kinetic friction?
It is a kinetic friction since the balls are continuously moving.
Okay, so do you think that the ball is rolling or sliding?
The balls will slide with some slight rolling.
Okay, so could you please turn to your setup page? There's a video about this.
I mean the video.
Yes.
This.
So does the setup, does your experimentation setup shakes when your experiment is over?
No, we try to fix it, and the shake you see is
this stick is this stick shaking.
You mean the whole setup shaking?
No, the stick on the plate.
You mean the plate is shaking?
Yes.
No, it isn't shaking. It's fixed onto the Lego set.
Okay. So please turn to page 35. So in the graph you use a linear trend line. So why do you use it?
To show that so this is like a boundary condition for, it's the limited coverage.
Okay.
Boundary.
So please turn to page 41, please. 41. What about the lower left? The findings on this top. Thank you.
Okay, thank you. Hold on, you have 3 minutes to prepare your.
Hello, juries and fellow competitors. I'm the opponent from the physics team at Student High School, and I'm going to oppose problem number 15, interpretation. And here's the problem statement. Place a few balls in a round container and investigate what parameters will change the rotating direction of the balls inside of it. And in the presentation, they mainly focused on the relationship between the amount, the angular velocity, the sizes, and the area of the bottom area. And so this is the reported structure. They started with an observation video and showed us the different rotating directions, and also they have their theory contains contains centripetal and the frictions. Then their setup is used with the EV3 and tracker, and for the experimentation, they investigate about the parameters of the numbers of the balls, the area, and the covering rate, and the angular velocity of the plate. And finally, their conclusion shows us some relationships between the parameters. And here are some strong points and weak points about the reporter. So first, they had a clear delivery, and they've got investigate adequate parameters. And also, they have not well explained why the friction is, what is the kind of is the friction, and also some error made in data analysis, and about the setup there, the video they provided cannot show if it is really shaking, because in our opponent's view, we think that it is a little shaky. And also their theory is not completed, just like what they say. And here are some points to be discussed, and reporter, please. So you say that the friction is the kinetic friction. So and you consider that the movement of the ball is sliding, but our opponent's view is that it is a static friction and the balls are rolling. Could you show us the video again? Oh, sorry. This is actually not to show my opinion. But because, so you think that the ball is always sliding? Always sliding.
Yes, I think the balls are sliding.
Okay. So where do you think the friction comes from?
Friction comes from between the balls and under the dish and on the outward of the dish tube.
Okay. So okay, fine. So just like what I mentioned, I think that your experimental setup is kind of shaky because the stick is not always like parallel to this one.
Well, I believe it isn't shaking, and yeah, in our experiment, it didn't really shake, and for this video, it looks like it's kind of shaking, mainly because of the video quality isn't that great.
So did you use this video to analyze your experiments data?
Yes, we recorded many videos, and
so it's always like this, and it's some shaking of the camera.
yes, because we hand recorded it.
So in our opponent's view, I think we think that you can try to use, because you use Lego, so it is not hard to build a Lego like a table and put your cell phone or your camera on it.
Yes.
Because it is not that hard. And also, could you turn to your theory part? Like you mentioned for directions. Is that you mentioned in the starting stage, or it is during the?
It is during, not the starts, because in the experiments, the starting of the setup is not as stable and continuous as during the whole setup.
So do you think that there's difference between the four directions?
Between the four directions of the centripetal force, the difference is just how the balls will smash against the outward
wall of the plate.
Yeah, the wall of the plate.
So why did you choose to use four directions?
Because I wanted to show how when turning a full circle, so when we see here, when turning a full circle, that's the motion is, so each circle, the motion of like the black ball would be opposite direction in this case. So each, when it turns each circle, this moves a little bit up. So I don't think it is necessary to show the whole the whole theory of every circle, because every circle is basically.
So just like what you said, it is the same. So in our opponent's view, it is not necessary to use four directions too, because it's just the same. Like after lower, just rotate it and it is the same. So we think that it is not necessary to do this.
But I just wanted to show how when we turn one one circle, then we can just divide it easily into 4 different directions, even though that's, well, for the black ball here, the whole circle, the 4 different directions of the centripetal force acts the same, but for the black ball, it has a different movement in each frame.
Oh, okay. So, do you think the black ball will move everywhere in the plane?
Can you say that?
And do you think the black ball will move to another place, every place of the place, when you do this longer?
Longer.
Like,
So
do you think that the black ball is well enough to represent all the balls?
Yes, I do believe the black ball is enough because the black ball can move in many different areas of the dish.
Okay. So, can you predict the boundary condition of the coverage rate?
Can I predict?
Like you've mentioned, it is like 44 or 45. And could you explain why it is 44 or 45?
Can I explain? How I explain this is that the ball coverage rate isn't less than the minimum ball.
So what is the minimum ball count?
It's this 30, 36, 20, and 12.
Why? And why is that related? How is that related to parameters and why?
The parameters is how large the ball is, so small, medium, and large. So they have different limiting coverage rates.
So what I mean is like what parameters decided this coverage rate number to 54, 45?
The ball size.
And any other ones?
Well, by changing the ball size, we change the radius, and by changing the radius, we can result in different limiting coverage.
Just like,
Am I missing your question?
Like what I mean is like, could you predict if I put a random plate and give you the radius and the friction coefficient? Could you tell me? Could you predict the coverage rate on the condition of this? Like we want to find a equation, and if we get all the parameters, and then
we believe that in theory this is linear. So we can use this line to predict, like, if you have a radius of 0.6.
Also, could you please send you the next page?
On next page.
That's one.
Last page.
Like,
You mean the page before what I just showed?
Yes. Why this is linear? Like the previous one you showed is linear, but this is not, I believe.
These dots have, like I just said, our corrections, so the collision of the balls and containers. So when we have less balls, then the movements will be more
stable, but not influenced by other factors. Do you mean like this?
Yes.
Okay. So what our opponent thinks that you cannot use a linear for this graph because it is not. Like it is become higher and lower.
Yes.
And you can also give us the R-square value of this linear line. Because it is a better way to get the accuracy of this linear line.
Okay.
So could we go back to the friction discussion? So do you think there's only sliding but not any rolling during the whole motion?
I believe that there is rolling motion.
you believe. So if there's a rolling motion, it cannot be a kinetic. It could have it cannot be a kinetic friction.
But I said that I think it's sliding with a little bit of rolling.
So you think that is a sliding and rolling mixed motion?
Yes.
So like what is the rolling direction each ball?
And the rolling direction of each ball mainly is affected by how the plates rotate.
So you think that, and also you think that the friction causes the rolling motion. So the ball and balls also have frictions. Does that affect the rolling motion?
I think that the balls between the friction between the balls won't affect rolling friction to a very large amount because there are a lot of balls.
Yes.
And each ball has a friction force like here, and they are when we use vectors to represent them, then they can add up to a value of almost none.
But why? Because what I think is that when the numbers of balls add up, the centrifugal force of the black ball is for the normal force, for the centrifugal force formed by other balls, and it will form a normal force through the black ball. So I think that when you add up the numbers of other balls, the friction between the balls and balls will become bigger.
But you forgot to think about the direction of the friction between each ball, because like this is touching here and this is touching here. They have different directions of friction.
Yeah, but for the centrifugal force, they always come to the left.
They always come to the left.
Yeah, for the, like this photo, the other balls always go to the left because of the centrifugal
Okay,
force.
I'm sorry, time is up.
So
Opponent can summarize.
So from the previous discussion, we talked about some theory about friction, like if it is a static friction or kinetic friction. We've got some different answers about this question. And also I think they tell us that the experiment setup is not shaking. And for the theory, they say that they use four directions to show the movement when it is moving around. And they didn't give us a way to predict the coverage rate for the rotational direction. And they have also mentioned that it is their mistake to not let the betas become not linear trend and ours and thank you.
Thank you. So question from the viewer.
Honorable judges and worthy opponent, this is the debater from Team Waker as the reporter team. So first, I would like to ask both the opponent and the reporter, in regards to the fact that do you both believe that there shall exist a phase between rotation and counter-rotation? Reporter? So if so, what sort of phase? Because it was not mentioned in the presentation.
I think that between co-rotation and counter-rotation, there will be a line to divide these two.
Okay, and the reviewer,
I don't think so.
You don't think so? Okay. And I would like to ask both, again, the reporter and the opponent in regards to the boundary condition that you guys want to set for this experiment.
I believe that the boundary condition can be seen with the experimental results that we had here. So you can see that the linear prediction.
But the previous graph should have been linear.
I believe that's when we increase the number of data then.
Okay, thank you. And the opponent?
Could you just say
What are some boundary conditions that you think shall exist in this question?
I think that there is a boundary condition decided by every parameters.
Okay, could you go to page 18? Do you think friction should be constant in this case? Because you mentioned it was in your presentation. So I would like to.
Yes, I believe that.
Okay, and the opponent, do you think friction is constant in this case?
Like there are multiple frictions, so the summation of it is not stable.
So in regards to friction, does both the opponent and the reporter believe there shall exist both static friction and kinetic friction?
Yes.
Yes. Okay. But you didn't mention static friction in your presentation, is that correct?
Because the balls are continuously moving, so.
Okay, and could you define what you meant by loose area and dense area?
So when we have balls that are around this area, then this half.
So it is not quantized.
It's a half, like this area.
Yes, but no actual value could be detected on this.
Yes.
Okay. And I would like to ask about whether you think there would be a vertical axis as the question mentioned.
You mean what?
Vertical axis. How do you think the vertical axis would be?
You mean the vertical axis out of the or?
The vertical axis.
Okay, I'm sorry, the time's up.
Thank you.
Review, you have 2 minutes to prepare your Okay, reviewer, please start.
Okay, so greetings, honorable judges and worthy opponents. I am the reviewer from Waker, and today I will be analyzing problem number 14. And without reiterating the question due to time constraint, I will be focusing on first, our team believes that the focuses should be set on first, investigate the phenomenon, then the parameters, and lastly, which the both sides failed to consider, determining the boundary condition. So the reporter has mentioned that the phenomenon includes when there are presented with fewer balls, it would be a rotation movement, and when more balls are presented, it will be a counter-rotation movement. The theory they included is that they believe that centrifugal forces and frictional forces cause the entire actions, and the experiment that they conducted matches with their theory predictions. And some pros and cons in regards to the reporter is that the reporter was successful in mentioning and providing a clear graph demonstration for every single one of their theory introduction. The reporter as well successfully used clear charts to represent their results. They have really concise conclusion with supported results. And for the cons, their model actually failed to explain the phenomenon, especially when it comes to frictional forces. And the experimental setup is not accurate enough. For instance, they included Lego balls, which could not really be considered as a ball, and the GIF that they provided are clearly shaking, but they said it's not shaking. And they have no enough data, for instance, a trend line with only 3 dots to support, and thereby making the graph and the model erroneous. And lastly, they have provided a lack of quantitative data. And in regards to the opponent, they asked several on-point questions that directly points out the flaws that existed in the presentation of the reporter. However, for the cons, they focused on too much irrelevant details in regards to this question. And to sum up the discussions, so first it's about the shaking plates. And the opponent asked whether shaking plates would cause errors or not, and the reporter replied that many videos were presented in order to do the analysis. However, we believe that the plate is clearly shaking as mentioned in their video, and it will affect the tracking of the track. It will affect the tracking of the tracker, like the app. And Lego bricks should not be used as it's not foliable, but we think marbles could be used in order for that. And second discussion was about 4 directions. The opponent believed that it is not necessary, but the reporter believed that it would be necessary. However, we do believe that 4 directions are really important in this case, and we believe that a multi-dimensional direction could be considered in this case. Discussion 3 was about the trend line on page 35, in which the opponent believed that it should be a linear regression graph, where the reporter believed that it should be a linear graph. However, we believe that it is neither the linear graph nor linear regression graph, as it should be focused on the exponential trend line instead of regression or not. And fourth is about rolling motion. While the reporter believed that rolling motion is inclusive and sliding motion is inclusive, the opponent only believed that rolling motion should be included. However, we do believe that both kinetic and static friction should be considered. And several points both missed by the opponent and the reporter is that first, they both failed to consider the fact that both static and kinetic friction exist. Second, they both failed to consider the boundary condition in regards to this case. And lastly, they both failed to explain the fact that there are a phase in which it should be the slowing phase that exists in between the rotation period and the counter-rotation period. And that would be the end of my report. Thank you.
Okay, thank you. Concluding remark from the reporter.
Okay, so to conclude this report, I explained my theories using a lot of graphs that clearly said how the balls moved and how co-directional and counter-directional are presented. And also we had charts that showed when there will be a change from co-directional to counter-directional. And the parts that I need to improve is the number of experimental data that can show that can be shown on the graph how the prediction is made. And also our theory about friction, static or kinetic or rolling, isn't clear enough to be good. And I will thank the opponents and the reviewer for your recommendations. Thank you.
Okay, thank you. Question from the jury. Okay. I want to ask, I think during the discussion, we'll discuss the friction is kinetic or static. Okay. There's two parts I want to ask you. First is, do you think if it's kinetic or you have a chance to separate these two? Okay. Is it possible to design the experiment to to see the kinetic friction is important or the rotational, the static friction is important. I think maybe we'll start from the.
We don't think that it is a very. We don't think that it is. Okay, we think that it is a. It should be measured the static friction coefficient and the kinetic rolling coefficient. And friction coefficient should be measured both. And about the friction force during the motion, because it is too complicated, because there are way many balls and there are many common points, so we cannot get a precise value of the coefficient.
How about you?
So the reviewer believes that friction exists on two levels. One is between the balls, and one is between the ball and the plate that the balls was put into. And in regards to that, the ball's movement on the plate would include both the spinning movement and the rotation movement and the rolling movement, in which that would cause there to be both inclusive of static kinetic energy and actual kinetic.
How about reporter? Do you agree with what they say, or you have some other?
I think that the balls in the container will be sliding and have kinetic friction, as well as between the balls there will also be friction. But due to the huge amounts of different vectors of friction, I believe that this friction cannot be calculated easily.
Okay, now let's go to the story section. Okay, let's go to the scoring station. Let's start from the reporter first. The pitch base, the score, 67676. And opponent is, which is your score, 66665. And reviewer.
刚刚的那个错了。
刚才从
再念一次，再念。
66667. Opponent. Okay. Then reviewer. Please. 78788. Okay. You want to make some comment?
好，我想可以用中文的了哈。
可以。
我想那个第一场哈，大家可能都会比较紧张一点哈，就希望我想大家其实那个多听了几场之后，你慢慢的也会找到一些那我想其实在这个比赛里面哈，可能实验理论可能要并重一点啊，因为可能刚刚大家也都有看到哈，有些人这个理论讲好多，然后实验一点点，有些人实验做了，但是理论切不进来，就希望大家可以尽量去把这个实验理论其实就像是研究里面的两个轮子，如果轮子是平衡的，那就会走很顺；那有一个很大的话，一定就是在那边自转往前走不了 所以希望大家可以把这个放在心里面那在你的那个 presentation 里面可以把它表现出来。
Okay. Yeah. Okay. Thank you. So let's close this first round fight. Okay. Thank you everyone. Okay.